In a spin wave, till now we have discussed the two important concepts. First of all, you have seen the classical derivation of dispersion relation of Magnons in first lecture, and in second lecture we have seen the quantization of spin waves. Now this is actually the last and third lecture on a spin wave. And actually in this last lecture we will see the two very important concepts regarding this spin wave. First of all, we will discuss the thermal excitation of Magnons. You know, Magnons are actually the quantum of spin waves. And after discussing thermal excitation of Magnons, then we will see the concept of a very important law which is due to Felix Bloch, and this is called actually Bloch T 3/2 law. So the subject matter of this present last lecture on a spin wave is thermal excitation of Magnons and Bloch T by 3 T to the power 3 by 2 law. Okay. Actually, this lecture will need some of the results which we have discussed in our first two previous lectures. And so you should remember those results for understanding the idea developed in this lecture. So I have mentioned here the two important results which will be needed in discussion of this thermal excitation of Magnons. In first lecture we have discussed the dispersion relation, and you have seen after getting the expression for general dispersion relation, we have find the dispersion relation particularly in case of long wavelengths. In case of long wavelengths of Magnons, you have seen that dispersion relation is like this. This is h bar omega equal to 2JESA square times k square. I hope as you have watched my previous videos on spin waves, so you are familiar with all the quantities used in this expression. Here you know h bar is actually the reduced Planck's constant, omega is the frequency of spin wave or Magnon, and Je, this is in fact the interaction integral, S is spin, A is lattice constant, and K is the wave vector. Okay. Now when we have discussed the quantization of a spin wave, then we have obtained a very important result which actually explains the quantization of a spin wave and this result is given like this. This Nk is equal to capital Nuk square over 2s. Here actually this Nk is an integer, you know, and it is equal to the number of Magnons of wave vector k. Okay, and n is the total number of spins in unit volume of the specimen, and Uk is the amplitude of a spin, kth spin wave. Okay, or a spin wave with wave vector k. Okay. In fact, while discussing the quantization of a spin wave, we have already seen that Magnons lowers the Z component of the total spin by 1, or in other words, each Magnon lowers the total magnetization by 1 unit of spin. Okay, and we shall now proceed to calculate the total number of Magnons denoted by this symbol summation over k and k. Okay, in all the states excited in the system at temperature T. And what will be that number? How we can define the total number of Magnons in all the excited states in the system at temperature T? That can be expressed as d omega z omega times average value of Nk. Actually here this z omega is what? This is just density of states, we can say. This is a number of states k per unit frequency range. For unit frequency range, what is the total number of states? That is represented by z omega. Okay, and this nk inside this angular bracket represents the average number of magnons in the state k. So let us see, if you want to find the total number of states in unit frequency range, okay, then what will be that number? That will be simply z omega times nk, because z omega is number of states in unit frequency range and nk is the average number of magnons in the state k. So nk times z omega, that will be given by the that is equal to the number of states in unit frequency range. And when we will actually multiply it by d omega, then this d omega times z omega times nk, that will represent the number of magnons in the excited state at temperature T having frequency between omega and omega plus d omega. In other words, you can say this product actually defines the number of magnons in the excited state in frequency range d omega. And when you will integrate it, then you will get the total number of magnons in all the states. Okay, so that's why this integral represents the total number of magnons in all the states excited in the system at temperature T. Okay, now actually our aim is to obtain the value of this summation over k and k, and for this you can see you have to obtain the value of this z omega and this nk. So after obtaining the value of z omega and nk and substituting in this equation 1, we will be able to find this total number of magnons in all the excited states in the system. Okay, so now let us try to find the values of z of omega and this nk. Okay, in fact, what will be the limits of this integral? Actually, when you talk about the limits of integral, actually this integral will be taken over all allowed range of k, and all allowed range of k means that will be taken for the first Brillouin zone. Okay. Now, if temperature is sufficiently low, then you know in thermal equilibrium the average value of nk is given by this Planck's formula. This is actually Planck's relation. Okay, I hope you have an idea of Planck's radiation law, and this nk is equal to 1 over e to the power h bar omega over kBt minus 1. So let us see, if we are talking about a very low temperature T, okay, and if this omega tends to infinity, then e to the power h bar omega over kBt, this will be infinity. And if it is infinity, then this average value of nk will be 1 over infinity, and that will be equal to 0. Okay, so actually the integral can be carried between 0 and infinity. And what's the reason behind this? Because as you can see from this Planck's relation, that the average value of nk tends to 0 exponentially, you can see, as omega tends to infinity. So the limits of that integral will be 0 to infinity. Okay. Now for finding the value of this z of omega, you have to think about the idea of lattice vibration. Actually, this Magnon is just equivalent to phonon, as in case of lattice vibration, the phonon oscillates. In this case of a spin wave, there is an oscillation of Magnons. Okay, so it is just analogous to the lattice vibration of phonons. Okay, and in that chapter, when you have discussed the lattice vibration, then you have seen a very important result which I have mentioned here directly. Actually, this Magnons has a single polarization state, or you can say a single polarization for each value of k. It means for a particular value of k, it will have one and only one quantum state. If its polarization will be 2, there will be two values of there are two states corresponding to the two polarization state. But as in case of Magnon, polarization is 1, and therefore for each value of k there will be only one state. Okay, and that's why you have studied in the chapter of lattice vibration that in 3 dimensions the number of modes of wave vector less than k per unit volume, this is given by this expression. This is the number of modes of vibration, 1 over 2 pi whole cube times 4 pi k cube over 3. Okay, so this is the number of modes of vibration, and as this z of omega is the number of states k per unit frequency range. So if you want to find the value of z omega, then you have simply to find the value of this modes of vibration for unit frequency range or for unit frequency. Okay, and for this we will have to differentiate it with respect to omega. So you can say that z omega is given like this. This is d omega. When you say d omega, it means you are talking about the number of modes of vibration per unit frequency range, and 1 over 2 pi whole cube times 4 pi k cube over 3. Okay, here this 1 over 2 pi cube, 4 pi over 3, these are actually constant factors, and so they are at edge. And when you will differentiate this k cube with respect to omega, what will be the result? That will be 3k square times dk by d omega. This is just a function of function. Okay, and therefore after simplification you can see this z omega is equal to 1 over 2 pi whole cube times 4 pi k square. This 3 and this 3 will cancel out, and times dk by d omega. Now for getting the value of this z of omega, first of all we have to find the value of dk by d omega. And you know, this dk by d omega can be obtained from the dispersion relation, because dispersion relation relates omega with k. And I have mentioned in the beginning of this lecture the relation dispersion relation for particularly for longer wavelength. This is h bar omega equal to 2 jes a square times k square. So using this result of this dispersion relation for particularly for long wavelength Magnons, we can obtain the value of this derivative dk by d omega. So as you have seen that from this dispersion relation we can write omega is equal to this much. This is 2 je times sa square over h bar times k square. And so you can write k square is equal to this much. Actually this value of k square will be also needed, because here there is k square, you can see. And as omega is equal to this much, so you can easily find this d omega by dk. What will be this d omega by dk? You can see this is in fact 2 jesa square over h bar times 2k. Derivative of k square will be 2k. That too has been multiplied here. So I have written 4 JESA square over h bar times k. This is the value of d omega by dk. Now here k is present and we can obtain the value of k from this equation 3, you can see. So k is equal to a square root of this much. This is h bar omega over 2 JESA square whole to the power half. Okay. Now this value of k we will substitute here to obtain the value of d omega by dk. So you can see that this d omega by dk is equal to 4 JESA square over h bar times k, and k is equal to this much. This is h bar omega over 2 JESA square whole to the power half. Okay. Now after simplification, you can see that this d omega by dk can be written as 2 times of a square root of 2 JESA square over h bar times omega to the power half. Okay. But in our equation for z of omega, there is dk by d omega, and we have obtained the value of d omega by dk. So you can easily say now that what will be dk by d omega, that will be 1 over 2, take the reciprocal of this much, and that and times h bar over 2 JESA square whole to the power half times 1 over omega to the power half. Okay. Now we will substitute the value of this dk by d omega from equation 4 and value of k square from this equation 3 in equation 2 to get the value of z of omega. So instead of k square, we will write this much which has been defined in equation 3, and instead of this dk by d omega, we will write the value which has been defined in equation 4. So substituting these two values, you can find z of omega is equal to this much. This is 1 over 2 pi whole cube times 4 pi h bar omega over 2 JESA square times 1 over 2 square root of h bar over 2 JESA square times 1 over omega to the power half. Okay. And after simplification, you can see algebra is simple. Z of omega is equal to 1 over 4 pi square times h bar over 2 JESA square whole to the power 3 by 2 times omega to the power half. Okay. So in this way, applying the dispersion relation, we have obtained the value of this z of omega. Okay, z of omega. Now, as I have told you, for finding the value of average value of nk, total value of nk, now we need the average value of nk, which is the average number of magnons in the state k. And for this, we will use the Planck's formula, as I have told you earlier. We know in thermal equilibrium, the average number of nk is given by this formula, which is actually called Planck's relation. This average value of nk is 1 over e to the power h bar omega over kBt minus 1. Okay. So you now know the average value of nk. You also know the value of z of omega. Now let us substitute these two values in our original equation to find the value of summation over knk. Okay. After substituting these values, you can see 1 over 4 pi square times h bar over 2 JESA square whole to the power 3 by 2 is a constant factor. So this will be outside of the integral. And inside the integral, the factor is omega to the power half d omega over e to the power h bar omega by kt minus 1. And we have seen that the limits of integral will be 0 and infinity. Okay. Now actually, to get the value of this integral, we will cast the integral in a standard form. And for this, let us substitute x instead of this h bar omega over kbt. Okay. As x is equal to h bar omega over kbt, so you can easily say that this dx will be equal to h bar over kbt times d omega, or d omega is equal to kbt over h bar times dx. Okay. So now instead of the variable omega, we will use x, okay, by this relation. Now let us check the limit. What will be the limit when we will change the variable omega in terms of x? The limits will remain same or different. Let us check. You can see when omega is 0, here the limits in this equation are for omega. So when omega is 0, you can see from this result that x will be also 0. And when omega is infinity, then x will be also infinity. So limits will remain same. Okay. Now let us use these results in this expression, and let us simplify it. So you can see summation over nk over k, that will be equal to 1 over 4 pi square kbt over jesa square whole to the power 3 by 2 times integral 0 to infinity x to the power half over e to the power x minus 1 dx. You can do the algebra. Now actually this integral is a standard integral, okay, and the value of this integral is obtained on using the table of standard integrals. So when the table of standard integrals is used, it is seen that the value of this integral is equal to this much. So you have to remember it. For your examination purpose, you must remember this result, okay? Because I have not done this integration here, and that is not needed. That will be a lengthy mathematics, and so you must remember it for your examination purpose, okay? So this integral is seen from the table of standard integral. This is equal to 0.0587 times 4 pi square. Okay, so the summation over k and k comes out to be 1 over 4 pi square kbt over 2 jesa square whole to the power 3 by 2 times this much. Okay, and therefore you can write that summation over k and k is equal to 0.0587 times kbt over 2 jesa square times 3 by 2. Here this 4 pi square and 4 pi square will cancel out. Okay, you can see this is actually the result which gives the total number of magnons that are excited per unit volume of the ferromagnet or crystal, okay, at temperature T. And from this you can see that the value of this number of magnons depends on temperature. It is actually this summation over k and k is actually proportional to T to the power 3 by 2. Okay, so if we take T equal to 0 Kelvin, what will be the value of this summation nk? This will be simply 0. It means at absolute 0, no magnon is excited. Okay, no magnon will be excited. No magnon will be found in excited state at 0 Kelvin. And this is an obvious result, because with increase in temperature, the magnons get excited into the higher energy levels. Okay. Now, after getting this value of number of magnon at temperature T in excited state of per unit volume of the material, now we will see a very important concept of spontaneous magnetization at temperature T. And in this discussion we will see a very important law which is called Bloch T 3 half power law. So now let us see. This is the concept of a spontaneous magnetization, or you can say Bloch T to the power 3/2 law. Actually, you know that at 0 Kelvin temperature, all the spins are parallel to one another in a ferromagnet. Okay, and in this condition, the magnetization is at its highest level, which is actually called saturation magnetization. Okay, you have learned this thing several times earlier. Okay, and this saturation magnetization will be equal to N times S. Here S is the value of each spin, and this N represents the number of atoms per unit volume. So the total magnetization at 0 Kelvin temperature will be equal to Ms, which is called saturation magnetization, and that will be equal to N times S. You know it. Okay. But when the temperature is raised, it is higher than 0 Kelvin, then you know spin waves are excited, and quantized spin waves you know are called magnons. Okay, and you have learnt earlier that each magnon lowers the magnetization by 1 unit. You have already learned this thing in the lecture on quantization of a spin wave. So each magnon lowers the total magnetization by 1 unit of a spin, and therefore this equation A, okay, this equation A, which represents the total number of magnons, okay, and each magnon lowers the total magnetization by 1 unit. So if there are this much number of magnons, so this also represents the reduction in total spin. Okay, reduction in total spin, and therefore I have written here, you can see that equation A represents the total decrease in magnetization of the system. Okay, and so if you consider that delta M is the total decrease or total reduction in magnetization, then what will be that? Ms, you know, this is the maximum magnetization which was at 0 Kelvin temperature, and at temperature T, when the spin wave gets excited, we consider that magnetization becomes M. So what is the reduction? Reduction will be Ms minus M, which we have assumed delta M. But as the total decrease in magnetization is equal to the total number of magnons in excited state, and total number of magnons in excited states is summation over K and K. So delta M is simply equal to this summation over K and K, and we have already obtained the value of this summation over Nk here in this equation A. So you can say that reduction in magnetization represented by the symbol delta M, which is actually equal to Ms minus M, that will be simply equal to 0.0587 times kBt over 2 JESA square whole to the power 3/2. Okay, I think you have clearly understand this idea. Okay, now as we know the decrease in magnetization here, and if you will divide this decrement of magnetization by its original value, then you will get the fractional decrease. And what is the original value of magnetization? You know, original value means value of magnetization when no magnon was excited, and that is the case of 0 Kelvin temperature. And at 0 Kelvin temperature, you know the magnetization is simply equal to the spontaneous saturation magnetization Ms. Okay. So when we will divide this delta M by Ms, we will get the fractional decrease of magnetization with temperature. And this will be given as delta M over Ms. But delta M, this is 0.0587 times kBt over 2 JESA square whole to the power 3 by 2. And Ms is equal to N times S. So this is the value of delta M over Ms. And it is obvious from this result that this delta M by Ms is proportional to T to the power 3 by 2. Okay. Actually, this result is due to Felix Bloch, and this is known as Bloch T3 Hall power law. Okay. This is Bloch T3 Hall power law. Actually, it is found that this law holds good at lower temperatures. We will see at the end of this lecture that at higher temperature, this Bloch T to the power 3 by 2 law badly fails. It does not agree with the experimental result when temperature is high. But at lower temperature, it agrees with experimental result. So you can say that this Bloch law is valid only at low temperatures. Okay, only at low temperatures. Now we will cast this equation B, which is actually the Bloch law, in another form. Okay, and for this you can see again this delta M over Ms, where delta M, this is Ms minus M over Ms, and that is equal to this much. You can see this equation B. Okay, now divide the Ms minus M by Ms separately, then you will see it is 1 minus M over Ms, and that is equal to this much. Okay, this much. And this N times AQ, that is written as Q by the symbol Q. N into AQ, it is written as Q. Here Q has a value of 1 for the simple cubic lattice, and this Q is 2 for BCC lattice, and it is 4 for FCC lattice. You should remember it. Okay. So 1 minus M over Ms can be written as 0.0587 times Qs times Kb over 2 JES whole to the power 3 by 2 times T to the power 3 by 2. Okay. And therefore, you can find the value of magnetization at temperature T, and this will be equal to Ms times this much. Ms times this much. This is actually the another form, mathematical form of Bloch T to the power 3 by 2 law. So this result is also known as T3 Hall power law after Felix Bloch. Okay. And you can see that magnetization is temperature dependent, as we have seen also in case of Weiss theory. Okay. Now we are going to see this the temperature dependence of the magnetization, okay, predicted by this Bloch law. And for this, let us see this figure where I have shown a graphical plot of magnetization M in against of temperature T. Okay. And from this figure, you can see that the results of experiments and of the independent spin model of Weiss have been also shown here. Okay. Actually, this full line curve, this is due to Weiss theory. Okay. When you say Weiss theory, that is actually for the independent spin model. Okay. Not a spin wave. and this dotted line uh, is for spin wave theory. Okay, this dotted line, and these small dots, these represents the experimental data. Okay, and you can see that when temperature is low, then the experimental result and the spin wave theory actually agrees with one another. But at higher temperature, there is a deviation. At higher temperature, the curve due to spin wave theory deviates from the experimental curve. Okay, but even at higher temperature, the curve for Weiss theory, which is a full line curve, actually matches with the experimental curve. So in fact, it is observed that the law holds with remarkable success at low temperatures. Okay, this is spin wave theory, but not at high temperatures. Okay, why this law does not hold at high temperature? The reason behind this is that at high temperature, a high density of magnons is created and the assumed spin wave model breaks down. Okay, this breaks down. And from observation of this figure, you can see that Weiss theory, which is actually independent spin model, is in close agreement with the experimental data as compared to the spin wave theory, okay, which we have discussed in this video. Okay, so you can say that spin wave theory does not agree with experimental result at higher temperature. Okay, but at lower temperature it fits with experimental result well. So in this way, our concept regarding the spin wave is now completed after the 3 videos on it. And so I hope after these 3 videos you will learn each and every aspect of a spin wave. Okay, and in magnetism now we will start the new concept of in fact anti-ferromagnetism, okay, in our next video. Okay, thank you very much.